Okay, so good morning. Am I audible?
Yes, sir.
Yes, sir.
Okay, thank you very much. So we continue with our 12th meeting of Classical Mechanics 1 at CMI. Today is the 8th of September 2022. And last time we were talking about Newton's first law, and we just started discussing Newton's second law as well. So are there any questions before we continue? Of course, your first 3 assignments have been graded and returned to you, so they're all available on Moodle. Okay, so if not, let us proceed. Yeah, so recall that Newton's second law was the statement that in an inertial frame of reference, the acceleration times the mass of the particle is given by the force. So there are many ways to interpret this. One is to regard this as the force determining the motion of the particle. This is the canonical viewpoint. So the force is specified or somehow given to you, and your job is to find the acceleration of the particle from it, and thereby integrate it and find the velocity as well as the position of the particle at any instant
So how
of
will
time.
you define momentum?
Yeah, so momentum is defined in a very simple way. It is simply mass times the velocity or mass times r dot. So, and mass is a fixed constant for a particle. It doesn't change with time. Yeah, does that answer your question?
Okay.
Yeah, there is no difference between these two equations. P dot is simply another name for mr double dot. I emphasize that m is not a function of time. We are studying point particles, and there we postulate that their masses do not change with time. One can study composite systems where there are many particles, or there is some subsystem which is losing mass to some other portion. Then you have to combine the equations for the many parts and get an effective equation for the total system. Yeah, or for some subsystem. That may take a slightly different form. Okay. Yeah. Now, I want to say a couple of things about this parameter m that appears here. It is a positive number. It is supposed that for each object, there is a mass associated. It is independent of time, and it is called the inertial mass. I will say why the name. Yeah, so we may now use Newton's second law to give a way of assigning inertial masses to bodies. So the idea of an inertial frame and Newton's second law gives you a framework, and within that framework, we can assign inertial masses to bodies. It is not as though the inertial masses of the bodies are already known to you or something like that. Yeah, you have to assign them in some consistent fashion. And one approach is to use Newton's law itself to assign the masses. Let me explain what I mean by that. We begin by selecting a reference body, to your favorite body, maybe this spectacles case. And we call it body A, and choose units in which its inertial mass is assigned the value 1. Okay, so we choose units in which its mass is simply 1, and we are free to do that. We can choose units that are convenient to us. Okay, then we apply a force to A. For instance, we may let a compressed spring push it. Okay, so we have this body and we let some force push it. a reference force. So a very specific force as determined by the elongation of a compressed spring. Yeah, and then we use a camera or some other device to find the motion of the particle as a function of time, where it is at each instant of time, and thereby determine its acceleration, and we record that. Okay, so we record its acceleration initially. So now we have done our basic job. Next step is that somebody gives you body B, whose inertial mass we wish to determine. Okay, so body B may be this mouse, and we wish to determine its inertial mass, which we have not assigned yet. So what we do is to apply the same force to it. By same force, I'm not saying we need to know the value of that force in some numerical sense. We just need to apply the same physical process. So if I had a spring pushing at my glasses case, I must do the same thing to this mouse. I must apply the same spring, compress it to the same amount and let it push, and then determine the trajectory of the mouse, and thereby evaluate its acceleration in the same fashion. So we will get some acceleration AB. Any questions so far?
We are applying the same force to both the reference body and the body whose initial mass we are trying to determine.
Exactly, that is the idea.
Do we
very
know the
much.
initial and the reference body? Do we know the initial mass of the reference body?
That question does not have an answer. We have assigned the inertial mass to the reference body, the value 1. Okay, we are free to do that. We are free to work in units.
Okay.
Yeah.
What will you take as the reference body?
That is totally up to you. See, some people in Paris like to keep one little metal piece inside some museum and call it the reference mass. I like to choose my glasses case. You may prefer your mobile phone. Okay, so it is totally up to you. Of course, we must have an agreement among each other which that reference mass is if we want to do comparisons, right? I mean,
so there is no restriction, right?
no, there is absolutely no restriction. Yeah, it is a matter of convenience. It's a matter of convenience and community participation and social cohesion. It is that if you choose a body that is very unwieldy, then others cannot replicate that body, or you cannot go and give it to them. Yeah, so yeah, so yeah, there is no restriction on that. Well, of course, there are practical restrictions. I mean, if you choose a feather, that may be very sensitive to other forces, not just the spring pushing it, some wind and yeah, other things. So you have to eliminate such things. All right. So far we have taken a reference body, assigned a mass, inertial mass 1 to it. Now we have taken another body whose mass we wish to determine, found its acceleration AB subject to the same force. Then we use Newton's second law to assign the mass mb equal to the magnitude of AA upon magnitude of AB. Okay, so this is the key step. and I hope you will see why this is the case. According to Newton's second law, mass of the A body times its acceleration, R double dot, okay, I'll write it as AA, is equal to that force. Yeah, and similarly, mass of body B times AB is equal to the same force. That's the key thing, same force. So equating these two formulae, we discover that MA AA is equal to MB AB. And so we now take the magnitudes on either side. This is a vectorial equation, but we can take the magnitudes on either side. And since we have assigned the value MA equal to 1 in our chosen units, we discover that MB is the quotient of the accelerations, AA upon AB in magnitude. Okay. So this is a very simple but a very practical and operational method. It tells you what you need to do, and this procedure can be followed by anybody, and they can make improvements on it. I mean, after all, you may be not so good at calculating the acceleration. You may your camera may not be that good. Somebody may improve and use a laser and so on. In principle. All right. Yeah. Now I must tell you why it is called the inertial mass. That is again, I mean, the name is coming again from this equation. It is saying that suppose the force is fixed. Yeah. Suppose you have a fixed force, namely the expansion of a spring, the force exerted by that. Now, a body with a larger inertial mass will have a lesser acceleration. Okay. So a body with a larger inertial mass undergoes a lesser acceleration for the same force. Yeah. And therefore, it has a greater tendency to remain where it was. So in English, we would say it has a greater inertia. Yeah. So that is the reason why we call M the inertial mass. So the inertial mass is a measure of inertia. Yeah, and it's basically what I said in words. For the same force, you will produce a lesser acceleration if you have greater mass. That is all. Okay. Any question about this procedure? I would like you to think about what we have done. This is a way of thinking in physics. It is an important step we have taken about how you would assign masses. So this kind of procedure can be used in other circumstances as well. So it is worth bearing in mind. Okay, let me proceed to other aspects of the second law. There are no questions. Okay, so now we need to make further comments on this force. Now, usually the force is a vector field. Yeah, I mean, of course, if it is just a spring that is pushing a body, that force only acts where the spring is. But I mean, the force of gravity on massive bodies here depends on location, depends on height. Yeah, may depend on time even, but let's not worry about that right now. So generally, the force is a vector field at different points. Say this is my surface of my table. At different points, the force would, I mean, the gravitational force could vary. I mean, with height, it could vary. But in any case, it's a vector field, even if it doesn't vary very much. Yeah, so it could depend on the location of the particle. Now, to begin with, the force field may not be known to us. I may not know what the gravitational field here is. Yeah. So what we do is that we do experiments with particles above my table. We do experiments with particles above my table, observe their trajectories, namely measure their positions, compute their velocities, and thereby determine their accelerations. And then use Newton's second law to deduce what the force must have been at that location. Okay. So I hope you understand what is happening. I don't know the force, but I observe particles moving in different places. In each place, I find the acceleration, thereby determine what the force must have been. Okay. Having already assigned the inertial mass. So that is the first step. I've already assigned inertial mass to my body, my reference body. Then I do these experiments in different places with my reference body and thereby determine the force. Okay. So thereby deduce what the force field may be. Having done many such experiments, we develop maybe a formula or a picture or a bunch of arrows of certain lengths. Yeah, a picture of the force field. Okay, so this in practice, this is what you would do. This is called the inverse problem, namely the determination of the force from the observed motion of particles. Okay, so it's very important to understand the viewpoint here. We are using the motion of the particles to deduce the force present. Okay. Now, any question about this? And this is called the inverse problem. Inverse because it is using the acceleration or the motion of bodies to determine the force. Any question about this terminology? Okay, if not,
What if you're in a accelerating frame?
Please say that again.
Like it depends. Like this will only be done if you know you are in a inertial frame, right?
Yes, absolutely. This equation of motion, Newton's second law, is valid only in inertial frame. So all of this has to be done in an inertial frame.
But if you're okay, I got it.
Okay. So
Any force from the frame is dependent on the frame that you are in. So like, isn't that circular?
no, we have fixed some frame. You choose some frame for our convenience. It may be the frame of our lab in this room. Yeah. So, and we will address the question about how things change when you go to a different frame. That is coming up. There is nothing circular about this. We are determining the force field as seen in this room by observing particles moving in this room. So that is our first step. We will then extend to other frames or other places. Is that okay?
Yes.
Okay, fine. Yeah. So, okay. So let me go back to where we were. Having done this to our satisfaction, namely, we have mapped out the force field in this room. Yeah, I mean, this is a little bit, I don't want to draw too strong an analogy because there are some distinctions, but you can imagine on a sheet of paper, you have a magnet in the middle, some ferromagnet, like one you put on a fridge, and then you have a bunch of iron filings, which you sprinkle around this magnet. And then the manner in which the iron filings orient themselves, from that you can determine the nature of the electric force field in that region. Okay, so we are doing something very similar to that, but it's not a static situation. We are observing the motion of particles, determining their trajectory, acceleration, and thereby determining the force field. All right. So, but there is an analogy with this iron filing story as well. So, having done this to our satisfaction, I mean, that's very important to our satisfaction. Yeah, we have some finite number of experiments we can perform, a little bit of time, a little bit of energy. Yeah, so only based on that we can do something. Then, yeah, so having done this to our satisfaction, now we can turn the whole process around. Now we utilize Newton's second law for the force field which we have determined to make predictions of what a given particle may do when subjected to this force field by solving Newton's equation, with prescribed initial conditions. And the available information on the force field. Okay, so now we have found the force field in our region of interest. So it may point something like this. Perhaps something like this. We have, by doing small experiments, we have determined the force field, the lengths of the arrows, and so on. Yeah, having got this picture, we do something new. We now introduce a particle somewhere there. Having determined the force field, we know what force it's going to be subject to. And then we solve this equation and determine its trajectory. We will join the dots in a sense and find its trajectory. Yeah, we are taking a step forward here. Yeah, because previously we may have observed only short-term motions of particles and deduced the force. Now we are integrating the equation using the known force field and extrapolating that force field to points where we did not know it perhaps, and thereby determine the trajectory of a particle which we place according to our wish. Now, this latter problem is called the direct problem. By direct problem, I mean the problem of finding trajectories given a force field. So this may be done by two different people. One person may have mapped out the force field. Yeah, and then you give it your...
You say you studied the motion and the trajectories to find out the force. Now why again do the opposite thing?
Yeah, so okay, maybe I this takes...
confused.
You're a bit confused. Look, let's go back to basics, right? I'm just sitting in this room. I am not some all-knowing person. I don't know the force field in this room due to gravity. I simply don't know it. So how will I find it? I will take particles, some reference particle, and let it fall over here find its acceleration by viewing its motion. All right, by taking photographs, finding where it is at what time, and then computing acceleration. From the acceleration and the known inertial mass, I will find the force at that place. I will repeat this process in different places, thereby finding the force at many points, okay, in this room. All right, so having done that, I have got a picture of the force field. This is what that picture is. And at this point, I will say that the force has some magnitude, some 2. And here the force has some magnitude 3, pointing in a different direction and so on. And now we will do some extrapolation also. I will say between these 2 points, the force field must be somehow interpolating between those 2 directions. So it should point like that. Right? We are free to do such things also.
Yeah.
So like this, we get a picture of the force field throughout the region of interest by observing short time motion of particles. Okay, now that is called the inverse problem. It has been completed by finding a picture of the force field. Now somebody else comes
So
around
we
and
can find the trajectory using accelerations only.
no, see, true, you can, but what we did previously is only let the particle move a little bit. That's all you need at a point. You just need the particle to move a little bit, find its trajectory in that little, and this is a totally experimental procedure. You see how the particle moves. From that, you get the locations and then form a little small curve, compute its second derivative with respect to time, and then you find the acceleration there. From that, you deduce the force. Okay. Now, somebody may come and say, here is my particle. It starts out already moving in a certain manner. How is it going to evolve in future, not just for a small instant of time, but over a day or over 3 minutes? Yeah. Now, that problem is called the direct problem, where I assume that the force field is known, namely already determined by your painstaking experiments the previous day. And now I will put the particle here, or it may even start from, not from rest, but starting with some initial velocity. Yeah. The previous experiments may have all been done with a particle starting from rest. But now I may do a totally different thing. I start a particle moving. I mean, I throw a ball or something like that. And I want to know how is it going to move. For that purpose, I will use Newton's second law with the known force having already been determined and integrated to find the position as a function of time forever and ever, okay, into the future. Is that clear? The difference between these 2 procedures?
Yeah.
Okay.
It may be f of r comma t to f of r comma t bivariate function.
Oh, wait. No, I'm not supposing that the force is a function of time. That could be the case, but let us not complicate matters too much right now.
Okay.
Let us, to some reasonable approximation, the gravitational force of the Earth over here doesn't change day to day. Okay, so this latter problem, namely the determination of trajectories. By trajectory, I don't mean just one small portion of a trajectory. I mean the entire curve, the projectile motion or whatever else, maybe falling down, accelerating, and so on. Yeah, the latter problem of finding the trajectory given the force field is called the direct problem. Okay, so we have discussed 2 types of problem. The inverse problem is to find f from observation of acceleration. Okay, so that is the inverse problem. The direct problem is to find trajectory from force. The force is given to you, supposed to given to you. All right. Okay, so then what do? We then compare these predicted trajectories. The predicted trajectories are purely mathematically found, okay, because you have the map of the force field, you have the initial location, initial velocities. You solve that equation either by hand or by computer or whatever procedure, and thereby you get the trajectory purely through theoretical means, through mathematical means. Then we compare that trajectory, that predicted trajectory, with new observations of such a particle, and thereby validate our formula or picture for the force field. Okay. So we are validating the force field that your friend found the previous day. If discrepancies are found, we may need to update our formula for the force field. We may need to refine it, improve it, and so on. So in this manner, one goes back and forth between the inverse and direct problems. So I am telling you in practice in a very, very operational way how you would use the framework of Newton's second law and first law to do physics. Yeah, I mean, this is not all of physics, but at least in this very concrete context. Okay, so much for the notion of what are the forces and how do you find it. All right, so I've given you a practical way to think about it. Any question about this? Okay, if not,
Sir,
let us.
Sir, if we are given all the possible trajectories, but not the velocities or accelerations at any point, can we still determine the force field?
I mean, if you know the trajectory, then you are done. If you know the mass of the particle and you know the trajectory, so if you know the mass and the trajectory are r of t, then
no, not trajectory, as in the picture of the trajectory. I know the path the particle will take, but not the time at which the particle is at a certain position.
No, that is not adequate information. You need to know r of t. You need to know r of t in order to differentiate it twice. And only then will you get its acceleration as a function of time. And from that, you can compute the force. Yeah, using Newton's second law. But it is not enough to know the curve traversed by the trajectory, by the particle. You need to know its parameterization by time, by Newtonian time. That is the necessary.
Thank you, sir.
Yeah. Okay. Yeah, this matter will come up again later on. Okay. Any other question? Okay, so let me go to another aspect, namely the choice of coordinate system. So now let us first mention that in Cartesian coordinates, the trajectory is given by a triple. Okay, so r of t, it's a vector, it has three components. I could write them as x1, x2, x3, or if I prefer x, y, z, which are all, of course, functions of time. Then Newton's second law.
This is x2. You mean this is x square? X square.
Yeah. So this is called a superscript. So x1 is simply x, x2 is simply y, and x3 is simply z. Not second and third powers. So this is just a notation where the coordinate of a particle in a certain standard notation is given a superscript. You could work with subscripts. That is also fine, absolutely fine. You can say x1 is x, and x2 is y, and x3 is z. Yeah, that would be fine as well. You just have some agreement. And there is a general agreement in the mathematical physics literature that coordinates will have superscripts or upper indices. But it is not a matter of importance at this stage. So we don't need to worry too much about it. What I want to look at more carefully is the form of Newton's equation itself. Newton's second law can then be written in component form, because mx double dot is F in the x direction, my double dot is the force in the y direction, and mz double dot is the force in the z direction. So the three equations can be combined into a single equation for I equal to 1, 2, 3. So mx I double dot is equal to force ith component to the force. And I runs from 1, 2, and 3, which correspond to x, y, and z Cartesian coordinates. Any question about my writing it in this fashion? Okay, now it is important to understand that this component form of Newton's equation changes when we go from Cartesian coordinates to curvilinear coordinates, such as spherical polar coordinates or plane polar coordinates, depending on where you are. In other words, what I mean is that in spherical polar coordinates, the equation of motion does not simply say that mr double dot. Let's suppose we look at r, the radial variable. It does not simply say that mr double dot is equal to the component of the force in the rth direction. It is not simply f dot r hat. Okay, f dot r hat is the component of the force in the r direction. I hope you will agree with me on that. However, the mass times acceleration on the left-hand side is not simply mr double dot. In curvilinear coordinates, there are additional contributions. In a sense, we already know this. So let me just recall what that is. For instance, there could be terms involving products of first derivatives of the coordinates in addition to the naive second derivative acceleration terms, as we already found in plane polar coordinates. So let's go back and recall what we found in plane polar coordinates. We discovered in plane polar coordinates that the acceleration vector had two components. One was the radial component and the other was the angular component or azimuthal component. The radial component had two parts. One was the naive radial acceleration, but there was also the centripetal acceleration. And then the theta component had two terms as well. One was the sort of the angular acceleration, and then you had the Coriolis acceleration. So this is the formula that you very nicely determined in the previous assignment. Now, the idea is that you start with Newton's equation of motion, F equal to ma. This is valid both in Cartesian and polar coordinates. But if you want to write it in component form in polar coordinates, what you must do is take the dot product with r hat. Then you will get f dot r hat is equal to m a dot r hat. And for a dot r hat, you must substitute this part. Okay, so that will be mass times radial acceleration minus centripetal acceleration. So the radial component of the force can produce a change in the radial coordinate, but it can also induce a change in the angular coordinate. So that is very important to understand. Whereas the x component of force will only affect the x component of the position. So there are cross terms over here, there are mixing terms and so on. And that is precisely because r and theta hat change with location. Okay, so I am now emphasizing that the component form.
F dot r hat is the radial component of force.
Indeed, the force is a vector field. So I can compute its radial component at any location. That is called F dot r hat.
Okay.
And that needs to be equated to mass times the radial component of acceleration. And you are all quite sophisticated now that you know fully well the radial component of acceleration is not simply r double dot. Okay, that is incorrect statement. The radial component of acceleration has two contributions: the purely r double dot term as well as the centripetal acceleration term. So you have to account for both.
We could have also written that F equal to that thing m times r double dot minus r theta dot square r hat plus. I mean, you just dotted both sides and made the unit. I mean,
correct.
R dot dot r.
Right. See, no, you are quite right. I don't need to write component form equations. I can write the full equation. I can take the full acceleration and then multiply it by the mass. So this would be r double dot.
I get it.
Okay, good. So I just finished writing this equation.
Repeat that statement about the radial acceleration.
So all I'm saying is that, see, this comment actually is for people who are unfamiliar with what you did in the third assignment. Okay, so you are all sophisticated people. You know fully well that the acceleration vector in polar coordinates has two components, the radial and the azimuthal component.
The general acceleration vector. I got.
The general acceleration vector. And people who are less familiar with the subject may have some feeling that the radial acceleration is simply r double dot. That is not true. There are two contributions. So when you write the radial part of Newton's second law, you need to account for both. That's all we are saying. Any additional questions? Okay, so one practical strategy is that if you don't know the equation in polar coordinates, you simply start with the equation in Cartesian coordinates and then transform the equation from Cartesian to the desired system. Okay, so that is actually what we did even in problem set 3. We started the Cartesian one and then we transformed. So that strategy will always work. Okay, now I go on to another aspect. We have simply talked about an equation of motion, Newton's second law. That is not adequate. I have kind of informally said, but there is additional data needed to solve the equation. And that additional data concerns initial conditions. So I want to be a bit precise about initial conditions now. Now, being a second order equation in time, when I say second order, I mean MR double dot. Okay, that two time derivatives is what is meant by second order. Newton's equation requires both the initial position R vector and the initial velocity of the particle as initial conditions. Okay, so you need to know R at time 0 as well as the velocity at time 0. These two pieces of information are needed in order to solve the equation. So let's be a bit more detailed. For a particle with 3 degrees of freedom, such as a particle moving in this room, these would amount to 6 pieces of initial data. Because that is, when I say 6 pieces of initial data, I mean 6 real numbers, the 3 Cartesian components of position and the 3 Cartesian components of the initial momentum. See, by the way, one can always work either with initial velocities or initial momenta. Because the initial momentum differs from the initial velocity simply by multiplication by the mass. Okay, so that is some constant which you have already determined. Okay, so we need to specify 6 real numbers in order to have any scope of solving this equation. When I say solving, I mean evolving Newton's equation forward in time to determine the trajectory. So let me say that a little carefully. The knowledge of the current position and the current momentum determines the trajectory via Newton's second law. Okay, so this is the slogan. I need to know where I am and where I am tending to go in order to find my future. Okay, that is what it is saying. It is not enough to know where I am. Newton's second law is saying that I need to know also where I am tending to go at that instant. It's not enough to know that I'm here. I need to know that I'm moving a little bit this way. Then Newton will take over and tell you where you go. So bearing this in mind, we define, now this is a technical concept, we define the state of the particle as being specified by giving its instantaneous position and momentum. Okay, because that is the totality of information needed to determine the future. So we call those pieces of data, namely the initial or instantaneous position and momentum, together as specifying the state of the particle, the current state of the particle. So to summarize, the knowledge of the current state of the particle along with Newton's second law equation of motion determines its future evolution. And that future evolution is called its trajectory. Let us see how this is done in a very, very brief way. For instance, for a particle moving on a line, suppose only 1 degree of freedom, particle moving on a line, subject to a force field f of x. Then we have the equation of motion mx double dot is equal to f of x. Then we want to find the trajectory given if we know x of t and p of t at some instant of time, we know both the position and the momentum. Then at the next instant of time, we can write down what the momentum is. So for that we have to integrate the equation. So p dot was f. So if I integrate this or write it in difference quotient form, it will say p of t plus delta t minus p of t divided by delta t is equal to f. Okay, so I simply take it to the delta t to the right hand side and find that the momentum at the next instant is given to first approximation by the momentum at the initial time plus delta t, the initial the little time that has elapsed, times the force at the initial location. And similarly, we can find the position at the next instant of time by integrating the equation x dot is equal to p. P by m. So you get the same thing. You write the x dot as x of t plus delta t minus x of t by delta t. And here you write p of t upon m, multiply and get this. Okay, so we have shown it is absolutely essential that you should know x of t and p of t, yeah, in order to determine the values at the next instant of time. Yeah, that is why, I mean, this is a second order equation, so it needs two pieces of initial data. Any question about this? Okay, very good. Let us, yeah, so then I have used this term many times before. So the path of the particle r of t satisfying Newton's equation and initial conditions is called its trajectory. Okay, so this is what we mean by the trajectory. It is the path of the particle known as a function of time. So regarding Ryan's question, you need to know where it is at each instant of time. And it must not be just any old curve. It must be the curve satisfying Newton's equation and the initial conditions. If those things are met, then we call it the trajectory. Yeah. So of course, trajectories are oriented by arrows specifying forward time evolution. That is how we place the arrows on a trajectory. Okay. So this is about Newton's second law. Any questions?
What about Newton's second law in non-inertial frames?
That we will discuss when we come to a discussion on non-inertial frames. So please hold on. Now, after some time, we will talk about that. Yeah, so the summary is that Newton's second law in a non-inertial frame no longer takes the simple form F is equal to ma. Yeah, I mean, if F is some gravitational force, but you are viewing it from some rotating frame of a merry-go-round, then there will be additional terms in this equation which you need to determine. Okay, so that job we will address afterwards. Yeah, I mean, let me ask a question. Suppose a particle began here with this velocity and you integrated Newton's equation knowing the force and found some trajectory. Okay, so that trajectory may be something like this. Let me ask the question, can the trajectory as a curve intersect itself? Can it self-intersect?
No, because that would mean that two different directions of force at the same point, right? Wouldn't it?
Two different directions of force produce the same curve. Yeah, okay, you are raising an important question, but let us look at it a little carefully. See, this is where is this curve, first of all? This is a curve in this room. So what is it saying? I started here with this velocity and the particle moved in this manner. It reached this point at some time. It continued along.
Force field remains constant, right? Okay. Or it varies with time.
Okay, it's
Sir,
a
I
good,
think it can
good question.
intercept.
No, I mean, all possibilities are there. The force field itself could change with time. It may be independent of time. These are possible. Yeah, but even if the force field doesn't depend on time, the point is that at a given location, I mean, at a given location, you are given the force field, it points in some direction. Okay. But the direction of the force field only determines the direction of acceleration. It says you must accelerate this way. However, at that point, you may already be moving in some direction, which may have nothing to do with the direction of acceleration. Yeah, are we able to accept that? So it is not as though a particle will move in the direction of the force. No, at this location, the force may have some direction. But if you're already moving in some way, you tend to continue moving in that way the force will give you the curvature of that trajectory, yeah, how it tends to change that direction of the velocity. So to make a long story short, such a picture is possible.
Sir,
At a,
I
at a,
think one example is the motion of a charged particle inside a magnetic field with circular motion.
yeah, in fact, there are simple examples. Simply, okay, yeah, you have given an example of a charged particle in an electric field. That's true. That is a possibility. But there are other possibilities as well. Yeah, so but the main point is that at a given location, the trajectory can come back to the same location, but when it returns, if it has a different velocity, then you will have a non-trivial intersection. If it happens to return with the same velocity, then you will start retracing that curve. Maybe I should have asked that as a question to you. Yeah, so let's take the example of planetary orbits around the sun. For instance, suppose the sun is over here and the earth is over here at some instant. It goes along in some elliptical orbit, but then it actually returns to the same position. But lo and behold, it returns with the same velocity that it initially had. So then from that point on, it must retrace the same trajectory because it has the same state. It has returned to the same position, having the same velocity. So from then on, whatever happened before has to be repeated. Okay, so you will have a periodic trajectory as a consequence. So this is another example of a curve that intersects itself. Of course, this is a curve that retraces itself, so it is more specific than transversal intersection. Yeah, but there is no, it is not forbidden for a trajectory from intersecting itself. Of course, the intersection happens at distinct times. Is this okay? Any question about this?
So one thing, you said that trajectories are twice differentiable functions, right?
Yes, yes.
So,
Function of time.
Yeah, function of time. So if the trajectory cuts itself, there will it be differentiable at that point?
Oh, absolutely. See, the times at the intersection point are totally different. Okay, so the question is only whether this curve, I mean, differentiability is a local question, right? So I'm asking whether R of t.
Oh, so this is not a graph, right? Yeah, it's a trajectory. Yes.
It's a trajectory. Yeah. This is not the graph. No, this is a curve in space. Yeah, I'm not plotting R as a function of time.
Okay. Then I understand. There are two defined intervals of time. They will
there are two distinct instants of time. Yeah. So okay. So Anhad has followed, but if others have still questions on this, please do ask. Being twice differentiable is simply that this curve must be sufficiently smooth. That's all we are asking. It has nothing to do what the curve does much later. That's a separate question. And at that time, we have to again ask, is that curve sufficiently smooth? That's all we are asking. Any question? I think somebody spoke. Okay. If not, let me proceed to the next important idea. And this has to do with Galileo's relativity principle. So let us, as well as additional ideas, namely space-time homogeneity and isotropy of space. Okay, so I will talk about all these things one by one. Okay. Yeah, I hope you are clear about what we have discussed so far. Okay, let me go back here. So now I'm going to first discuss Galileo's relativity principle. So this actually predates Newton's laws, but Newton has incorporated it in his laws. Notice, oh, what happened? Notice that Newton's second law relates the force to the second derivative of the position along a trajectory. By the way, going back to Anhad's question or also others, if the trajectory looked like this, yeah, then it would not be twice differentiable, yeah, at this point. So if this was the trajectory in space, then there is some further discussion needed. Anyway, so we can discuss those examples later. Okay, so yeah, coming back, recall that Newton's second law relates the force to the second derivative of position along a trajectory as opposed to, say, the first or third or other derivative. Yeah, so this is what we observe from Newton's second law. And you may wonder why this is the case. This, that is the appearance of second derivative specifically, is to incorporate Galileo's relativity principle. So I have to introduce what it is. I will do it in several steps. Very roughly, Galileo's relativity principle says that there is no dynamical way. I will mention what I mean by dynamical way. Basically, through doing mechanical experiments, there is no dynamical way of telling if a frame is at rest or moving uniformly relative to an inertial frame. So this is a very deep observation of Galileo. He is saying that if you know that one frame is inertial and you consider another frame that is moving uniformly relative to it, then there is no way to detect that uniform motion by doing local experiments in the two frames. But let us understand this in more detail. Any question about the statement so far?
Sir, does this have anything to do with the argument, the discussion we had the other day where we said we can't really define what an inertial frame is, like with precision?
Oh, no. This is a different aspect. This is a different aspect. It is see, previously we were addressing the question of existence. Is this frame inertial or not? Okay. That was the question. And we were saying that you can do some experiments and find out whether the frame is inertial to reasonable accuracy. That is all. Okay. And with effort, you can make that precision better and better. Okay. So suppose you have done that and satisfied yourself and your friends and relatives that this is an inertial frame. Now, Galileo's principle is discussing the question of uniqueness, not of existence. Namely, are there other inertial frames? You have found one, you claim it's inertial. Can I find others? Okay, he is answering that question in a positive way. He's saying that there are other frames which are also inertial if one frame is inertial. In fact, Galileo is saying, I mean, I'm going to expand on this, but was that Anhad or who asked just now?
Sir, it was me, Kaustubh Manda.
Kaustubh Manda, sorry, I'm very sorry. Yeah, I have to still learn the voices. Yeah, so Kaustubh, yeah, so Galileo is basically claiming that inertial frames are not unique. And if you have one inertial frame, then another frame that is moving uniformly relative to it is also inertial. But I'm going to clarify that.
Sir, why is this? How will you justify this? That why there is no dynamical way of telling?
Okay, how will you justify it? By checking. I'm going to tell you how Galileo checked it. And Galileo didn't simply do this. He simply stay this. He tried it out and then deduced that this must be the case. And we are going to recall what he did. So just a moment. So in 1632, that is nearly 50 years before Newton's book was published, Galilei, by the way, from which country is Galileo?
Tally.
Italian.
Indeed, yeah. So perhaps the name gives it away to many of you. Galilei is from, is from Italy. He observed that it was not possible to detect the uniform motion. By uniform motion, I mean constant velocity motion without rocking of a ship relative to the shore. So this is an actual experiment relative to the shore by performing mechanical experiments under the deck of the ship. Okay, so you have a ship that's in the dock. Yeah, at the seashore. You do some experiments inside that ship in a room inside. What kind of experiments? You may throw a ball and ask how long it takes to come back, or you may throw a ball horizontally to a wall and ask how long it takes to come back, or in what manner, in what angle it returns. Yeah, these kind of experiments. Then, without telling you, that you sleep off. Then after the next day, somebody else has made that ship move uniformly in the sea, okay, and without any rocking motion. Yeah, just simply straight line, uniform motion. Okay, then you wake up, you don't know the ship is moving, you repeat those experiments. And what Galileo found is that the results of those experiments are exactly the same as what you got the previous day when the ship was at rest. Okay. Of course, you don't know that the ship is moving, so you would say there is no difference, right? So the person who made the ship move will now deduce that a moving ship and a uniformly moving ship and a ship at rest, the corresponding frames, the results of physical experiments done in both are the same. Okay, so this is what Galileo is saying. And the reason we said you should not do it on the top of the ship is because if you're standing on the deck of the ship, then of course you can look at the surroundings and know that you're moving. That is not allowed. You are supposed to do it inside a room without any windows in the hull of the ship or something. Okay. So, i.e., without looking out or by using external forces. You must not use external forces. Only forces like throwing a ball against the wall, those internal operations. I will clarify this further. In fact, let me say more about what these experiments could be, because I mean he says it very graphically and very beautifully. So these experiments could include observing the motion of projectiles, such as how long it takes for a ball thrown horizontally at a given speed to reach a wall. Okay, so this is a kind of experiment you could perform. It could also include the manner in which water drips from a jug. You keep a jug with some water inclined at a certain angle with a certain amount of water, and you see how the water drips. Yeah, I mean, the direction of the dripping, how much water drips, all these questions you can examine. You can even do other things like observe how flies move, how fish move in a little tank inside that place. He did all these kinds of things. And he found that there was no way to tell between a ship at rest at the shore, anchored to the shore, and a ship that is moving uniformly. Okay, so this is a very significant discovery that Galileo has noted and presented in his book. A dialogue between two chief world systems. It's an interesting book where he presents arguments, his argument, and I mean, it's all done in third person. He doesn't say what he's saying. He says this person is saying, that person is saying, and they two are having a debate, and thereby he conveys his ideas. Anyway, we'll talk about that another time. Now, I must say what Galileo is not saying. It is important to note that Galileo's principle is not concerned with forces external to the lab inside the ship. In other words, and external forces, I mean things like looking out using your eyes. You're not allowed to do that, because then you're using external influences. In other words, if the acceleration due to gravity varies with location, that's an example of an external force. It's a force external to the lab. Now, if that acceleration due to gravity varies from place to place in this ocean, which it can, if you may make a long trip, it can vary, then it would be possible for an observer in the uniformly moving ship to infer that the ship's frame is moving relative to the shore. Okay, because the acceleration due to gravity changed, then maybe the time period of a pendulum would change, or the manner in which bodies fall would change. And then you would infer that, okay, I have reached a new place, so I must have been moving. But you're not allowed to do such things. Galileo's principle only focuses on forces internal to that lab. Thus, Galileo's principle asserts that the relative motion of bodies in the lab, not the absolute motion of a body in the lab compared to things outside. We are not concerned with such matters. The relative motion of bodies in the lab is the same whether observed when the ship is docked to the shore or when it is uniformly moving. So is
So
the
why
state,
relative motion? Why is he considering relative motion?
no, those are the experiments he has performed. I mean, when you're inside a room, the only thing you can perceive are the relative things. Yeah, I mean, how far is my finger from the
I mean,
wall?
relative to me. I mean, the motion of the body is relative to me.
Relative to other bodies inside that lab. That is all we can observe. When I say relative, that's what I mean. I may have two balls, yeah, inside this room. This room is inside the ship. I can study the relative motion of these balls. I can study the motion of the ball relative to the wall of the ship. I can do such things. I can ask, yeah, that's what I mean by relative. I will write equations also shortly, but yeah, but please do ask if you have any question.
I mean, you can mathematically express these things.
Yes, it is
I
possible to
think
write mathematical equations and express it as an invariance of a certain equation. We will do that. Yeah, but it's important to realize that, I mean, it took a very long time for Galileo to enunciate these ideas. And even at that time, it was a little bit imprecise. It took a long time to make these things really precise. I mean, even the equations that we will write now were not really available to Galileo. I mean, he didn't even have Newton's second law, so he had only some rough ideas. So now this idea that mechanical experiments internal to the ship cannot detect uniform motion of the ship relative to an inertial frame. This idea is elevated to the principle of Galilean relativity, yeah, which states that the laws of mechanics must take the same form in two inertial frames that are in uniform motion relative to each other. Okay. So suppose, yeah, so suppose you have two inertial frames that are in uniform motion relative to each other. So you have checked that each frame is inertial, if you like. Yeah. And you know that one is in uniform motion relative to each other. Now we are reformulating Galileo's observation and saying that the laws of mechanics must take the same form in these two frames. Suppose that happens, then there will be no way, no mathematical way of telling the frames apart, because the equations are identical. Then you cannot know that this frame is moving at velocity u relative to that frame. Okay, so if that is the case, there is no way to do through mathematical procedures involving those equations to detect the motion of one frame relative to the other. Yeah. Any question so far? Okay. Yeah, I will restate this principle in a couple more ways and so on. Yeah, so there are different viewpoints, and I hope you will appreciate it and come to understand it better. But I do emphasize these are not trivial statements, and it does. I mean, there are many people who are confused about them, so don't worry if it takes you time to understand them. Okay, now this is just a parenthetical remark. The next one, we don't want to dwell on it now. But it turns out that Galileo's principle of relativity continues to hold in special relativistic mechanics. Okay, beyond Newtonian mechanics, it also holds in special relativity. However, some modification is needed, not to the principle, but to the implementation. And to accommodate the constancy of the speed of light, Einstein modified the transformation rule that relates coordinates in two frames that are in uniform motion relative to each other. Okay, so that statement is not understandable at present, but we will make it understandable later on. But the point I want to convey right now is that Galileo's principle of relativity continues to hold in relativistic mechanics. It is not something special only to non-relativistic theory. Okay. Any questions? Okay. Now, a couple of warnings or remarks. In Galilean relativity, it is assumed that the mass of a particle is the same in two frames that are in uniform relative motion. Okay, the mass of a particle is the same in two frames that are in uniform relative motion. Of course, you can check the consistency of the statement. You can, of course, you have a reference body which has been postulated to have mass 1. You will postulate that it has mass 1 also in a moving frame. And then you will take your new body B, whose mass you wish to determine. You will do the same procedure that I mentioned, apply a force to it, determine the acceleration, take ratios of acceleration. You can do the same thing both in one frame and in a moving frame and see whether the mass of body B comes out to be different. Well, it will come out to be the same. Okay, so this you can check the consistency of the statement. That is one thing. The masses of particles are the same in frames that are in uniform relative motion. Moreover, we will suppose that both observers use the same scale for measuring distances, and both observers agree on the time interval between any pair of events. So these are some technical conditions. We will say more about them. Let me restate it just briefly now. In other words, a uniformly moving measuring stick. So I have a measuring stick in front of me. I compute its length. Then suppose the stick is moving and I find its length by some procedure. Claim is that it would be the same as what I initially assigned. The same length. As when observed at rest. And that a clock that is moving at a constant velocity neither slows down nor speeds up relative to a clock at rest. Okay, so these assumptions are built into Galilean relativity and Newtonian mechanics, and one can justify these using these things with the sending light signals and so on. Okay, assuming the speed of light is infinite, you can justify all of these assumptions.
So what is this clock? I do not understand this part. A clock that is moving at a constant velocity.
Yeah. So, okay. Suppose I'm sitting here in this room. Outside this room, there is a railway track, and a train is going in that track, in that railway train at some constant velocity. Now, I have two clocks. Both are identical. Both have initial time fixed, same, synchronized. So one clock I keep with me, and one clock I give to the driver of that train, and it's going there. Now, suppose we have two events that we assign, and we say that the time elapsed between those two events, according to me, according to my clock on this table, is 2 minutes. Then I can ask, I can see the clock in the train, what time it showed at those two events, and ask whether the time elapsed is again 2 minutes. The claim is, or the requirement in Galilean relativity is that they should be the same. Is
Okay.
that, yeah, is that okay? Yeah. So moving clocks read the same time as a clock at rest.
Is this a very special fact?
Okay. No, see, I have a feeling I am saying certain things which are whose significance will become more understandable when we take a situation where it fails. Okay, and that fails in the context of special relativity. Yeah, I am, and we will discuss that later on in this course, and you will recognize the significance of this statement. And what, okay, I'm not spending too much time on this right now, because I feel that we should also do some other things. But one can check these statements. One can be more precise. What do I mean by the time elapsed between two events as observed in the moving clock? Yeah, I have to send a light signal from here at the first event, and then get it back. It will tell me what the time on that moving clock is at the first event. Similarly, at the second event, I should send a light signal, get it back, find out what the time is on the moving clock at the second event. Take the difference. Yeah. So you can set up a protocol. You can set up an operational method to find these times, and the claim is that the times are the same.
Yeah, I had a question. So suppose you are in a frame that is accelerating with respect to your surroundings on Earth, but you are within the frame. So if there was no friction or anything, would you feel that acceleration?
Yes, it turns out that it is possible to do mechanical experiments to determine accelerated motion relative to an inertial frame. Yes, so that is detectable.
But would you be able to determine if the frame is accelerating or not if you didn't know your surroundings?
Yes, absolutely. Without looking out. This is all without looking out, without looking at surroundings. Absolutely. We are not allowing for such things. So acceleration is detectable by local mechanical experiments without any cheating of looking outside.
Could you please give a example of such an experiment? Like what would change?
Yeah, I will show you. We will give examples because that is a matter we are going to discuss, uniformly accelerated frames. So that is a topic of interest. I am going to discuss in some detail. So the examples will definitely come there. Yeah, so just hold on a little bit. Yeah. All right. Let's see. So. But you already know such some of those things. I mean, when a car is accelerating, and even if you shut your eyes and so on, and all you can do is do experiments between the seat of the car and yourself and such things, it is possible to feel certain forces where your body presses against the seat and so on. Such forces are present. Such effects are there, which will tell you that the car is accelerating relative to the road. And on the other hand, when the car is at rest or the car is moving uniformly, those forces will be absolutely not seen by you. Okay, so these are the kinds of effects which you will be able to see and determine that a frame is accelerating. Anhad, is that okay? Very briefly, at least.
I'm sorry, I lagged out for that. Could you repeat it?
Yeah, okay. Okay, so since we are talking about this very briefly, I claim that if you have a car at rest and you're sitting inside on the seat, you will have certain sensations, right? Yeah, okay, the seat presses against your back in a certain manner. Yeah, that kind of thing. And your eyes are shut, the windows are shut, you're not looking outside. Now, suppose you go off to sleep and then somebody starts the car and moves it at a constant velocity. Then you wake up, then you ask yourself, is the sensation on my back the same as what it was when the car was at rest? Claim is the sensations are exactly the same. You cannot tell that the car is moving uniformly. That is what Galileo is claiming. Okay, so you can, of course, check it. You check it and see whether the feelings of the car seat on your back are the same as when the car was at rest. Okay, so this is Galileo's first claim. Now, the second matter concerns accelerated motion of the car, right? So now the car starts accelerating. Yeah, you step on the accelerator pedal, and now you ask again, is the sensation on your back due to the interaction with the seat different than when it was at rest or at uniform motion? I claim you are all familiar with a new sensation that you get when the car is moving. I mean, car is accelerating. So through this procedure, even though your eyes are shut and you are not the driver, you are not pressing the accelerator, you can still determine that the car is accelerating. And it's not just for accelerating in a straight line. Even if the car is maintaining its speed but turning a bend, it is possible to determine that the car is accelerating. You are familiar with such things, I think. Is that okay, Anhad?
Yes,
okay, fine. So, all right. We are now basically out of time. So I was going to explain to you how the appearance of second derivative term in the equation of motion, Newton's equation, can be motivated using Galileo's relativity principle. Okay, so there is a very concrete way to understand why Newton's second law has to be second order in time if it must incorporate Galileo's relativity principle. So I will do that the next time we meet, namely on Tuesday. Any other questions right now?
Yes, I had a question. Suppose that we were in space, right? Like no friction, nothing. We were in space, and okay, so but we were really close to like a planet. So like the gravitation of the planet is pulling us towards it, right? Because of gravity. So would we be able to feel it the same way we feel acceleration in a car? Would we be able to feel being accelerated due to that gravity?
Yes, it is possible to feel that. Yeah, yeah. Yeah, I mean, the acceleration due to any force, be it a frictional force or the force due to gravity or the force due to an automobile propulsion, whatever the source of the acceleration, it is detectable. Yes.
Why do we feel it?
You have to do such experiments. You have to do an experiment where there is no such acceleration present. See what kind of effects you see.
Oh,
and,
no.
and then repeat those experiments when there is a planet that has been brought near you. Okay, so one has to arrange such a situation and compare the results of the experiments. By compare, I mean how long does it take for a ball to fall from here to my table within my little room without looking outside. Yeah, and do compare that with when I have some acceleration, some external force due to, say, another planet and so on. Okay, so by comparing these things, one can determine. On the other hand, the assertion is that you cannot determine uniform relative motion. This is the deep insight of Galileo, which underlies Newton's second law. The character, the mathematical character of Newton's second law, being a second order equation, has a direct it directly follows from Galileo's principle of relativity. And I will explain that next time. Any other questions?
Sir, this is not a question, but a request.
Yeah.
Sir, I would need to be traveling to CMI on the 7 days from now, on the next Thursday. Please give me an additional chance to give class quiz or something like that if something happens on that day.
Okay. All right. I will take your request into account. All right. Fine. I mean, I am not accepting you from your duties, but yeah, I will bear that in mind. Sure. Any? I thought somebody else had a question.
That we cannot detect uniform relative motion mechanically, right?
Yeah, through mechanical means. You can detect it through other means. Simply open the window and look outside. Yeah, that is also possible. Yeah. No, it's very important to know what procedures are allowed and what are not allowed. And by making that restrictions, you discover laws of mechanics.
And those the assumptions you wrote in Galilean relativity, you will understand the significance by studying special relativity.
No, see, that was only an excuse on my part. It is possible to justify these assumptions of Galilean relativity by doing carefully managed experiments, by sending light and so on, assuming speed of light is infinite. So you don't need to know anything about special relativity to appreciate these ABC. However, the significance of ABC will become very stark and obvious to you when we discuss special relativity. And so I prefer to do it in that context. Yeah, just.
So you mean that there will be situations when both observers will not agree between the time on the time interval between.
Exactly. So it will become very obvious that two observers in relative motion even uniform relative motion will not agree on the time elapsed between two ticks of the same clock. Yeah, just the clock in on the train driver's hand. Train driver will say it elapsed 2 seconds. I sitting in my room on the ground would say no, it took some other time. Okay, so it will become obvious that these two are not the same. Yeah, and that those differences will go away if the speed of light is infinite. Okay? And then we will come back to Galilean relativity. So by that argument, it will be possible to see where the assumptions ABC sort of fail. Any other question? Okay, if not, thank you very much for all your questions. Please do think over these things we have spoken about Galilean relativity and second law of Newton. We shall meet again on Tuesday. Thank you.